Welcome to another video explaining the universe using the particle model. Well, this is another video explaining the senses using the particle model. I've already held one on how hearing happens, part 1. This is part 2. And we'll try to cover the rest of this explanation in this video. And as usual, I've been using the Howard Hughes Medical Institute series that was made in 1997. And it has 4 different videos. This is the link to it if you want to watch them. And I've covered 1 and 2 already, and this is the second part of how hearing happens. And recommend you watch these videos. Okay, a little bit about the bandwidth of human voice and high definition audio. I worked in telecommunications designing digital switches, and one of the things you become very familiar with is the bandwidth of the human voice. Well, old phones, I'm not sure why they say that, but that is typically the bandwidth of the speaking voice. However, what's interesting, when I was looking around and I found curves like this, one of them actually said that this becomes important not because of, which includes our speaking voice, but also our singing voice. When we sing, there are frequencies up in this range, up to 7,000 hertz. But the ear actually has a bandwidth, a detectable bandwidth of 20 kilohertz, and maybe we can hear these frequency out here because other objects, other animals maybe produce frequencies that are higher that the ear and the brain need to understand or hear. So this is the bandwidth. Generally speaking, we cover this in telephony as a 4 kilohertz bandwidth channel, kind of beefing it up from 0 to 4 instead of this just narrower band. And last time we showed the ear, and of course the sound enters through the ear, the canal, moves the drum back and forth. You got the hammer, anvil, and stirrup, which in turn push the cochlea. This is the cochlea, in which there are hair-like receptor cells that are really the point at which the sound is generated and sent to the brain. Now, the speaker in this third video from the Howard Hughes Medical Institute clearly talks about the fact that the cochlea, when it's spread out like this, is actually doing a Fourier analysis. Now, you start out with a constant pressure on the eardrum at 14.7 psi, and the eardrum moves back and forth, causing the hair bundle to move back and forth to generate these signals, high frequency at the narrow, thinner part of the cochlea and lower frequency here. And the higher pressure causes the basilar membrane. This is kind of representing the basilar membrane that moves up and down. And the high pressure appears to cause well, no, that's what it said last time. It causes the basilar membrane to move down, and hence you see this moving down and then up, down and then up. And generating, and it analyzes a complex wave at any instant of time, and various parts move up or down, sending corresponding signals to the brain. It actually seems to be doing a Fourier analysis, but it's not doing math. This is a physical representation of how math would have done it, but it's not mathematic. We're not looking at plus, minus, integrals, summations, or whatever. So if the cochlea does a Fourier analysis, this is a typical example of what might happen. You don't often get a square sound wave, but I found this diagram for a square sound wave. And the cochlea is going to, in a square wave, is going to find all these odd harmonics. The primary amplitude 1 here comes from the first harmonic, which is the main basic sine wave that progresses like this. And then it also contains a third harmonic, which has 1/3 the amplitude, and the fifth harmonic, 1/5 the amplitude. You can see it's precisely on 1/5, and that progresses that way all the way down. But the cochlea only has a 20 kilohertz. So if this were 1 kilohertz, this is 3 kilohertz, 5 kilohertz, 17 kilohertz, 19, and 20. But the cochlea does not do these top two. Does the first 10 of the square wave, which gives a, if we actually do that, it gives a pretty good square wave. And the cochlea does this by virtue of the sound wave moving the drum back and forth, and the membrane, the basilar membrane, moving up and down. Generates 10 different, and they're going to be spaced logarithmic along the length of the cochlea. Okay, interesting. Well, then the brain does the Fourier synthesis. The cochlea does the analysis. The brain receives these 10 sine waves, and it sums them. This is an equation that would take all of those over at any instant of time. You pick a time, plug it in, then you sum from 1 to 19. From n equal 1, actually it's from 1 to 9, or 1 to 10. To get the 10 components, and it'll give you this, mathematically give you that. Brain does the same thing. Somehow it takes these, and these signals, each of these is an individual signal to the brain. The brain gets the signal and makes a composite. It sums it in its own way, and we hear the square wave. I've never heard a square wave. I'm not sure what it would sound like. Well, the question is, how often does the brain receive these signals? And I mentioned it was instantaneous there. You could pick any time mathematically. But the first, the video in this series that we talked about indicated that a repeat time of a pulse. It talked about a pulse. This was for the olfactory sensory system. And the repeat time of a pulse in that system was about 1 millisecond. You get the pulse, and then it's got to recover and stabilize before it does another one. That's 1 millisecond to do that. Well, let's see what that means. If I can move to the next one. Let me talk about sampling theory. The digital telephone systems require that sound be converted to a digital code. It's called pulse code modulation, or PCM. The voice we generally allocate that 4 kilohertz bandwidth that you saw earlier to cover the 300 to 3400 hertz. Well, there's a sampling theory that Nyquist made, and it states that to produce a high quality signal, voice or any signal must be sampled at a rate that is twice the highest frequency. Well, if the highest frequency is 4 kilohertz, then you have to have a sampling rate of 8,000 hertz, which means it's sampled every 125 microseconds. And I can tell you for sure that there is a codec in your phone, your cell phone, that has a sampling rate of 125 microseconds and converts your voice, that when you talk into it, every 125 microseconds, it generates a PCM code, and it sends that digital code to the other end where it's converted from code to voice. It's called a codec, coder, decoder. 125 microseconds. The ear has a bandwidth of 2,000 hertz. So we're told by this video by Howard Hughes Medical Institute. So the sampling rate must be 4,000 times a second or every 25 microseconds. That's a fourth of a millisecond. A pulse needs a millisecond to recover. So if you're going to reproduce sound and have it sampled at least 25 microseconds, that doesn't work. So I conclude the brain gets a signal continuously, sending the signal to the brain at the speed of light at every instant of time. So the sampling rate of the brain is quite high, and minimally has to be every 25 microseconds, but clearly I don't know that the brain works that way at all, but it must sample at least that often if it's going to produce a 4 kilohertz, or if it's going to produce, a 2,000 hertz signal sound in your brain. It would have to be at least that fast, but I'm guessing it's continuous. So what would that electrical signal look like? Well, most times when you look at, now I'm not at a square wave, I'm looking at a sine wave, maybe 1,000 hertz, that's going like this. And when you mathematically describe this in those equations, by the way, that I saw where it was summing, you end up with a midpoint of 0, a plus 5, maybe magnitude of number of electrons or G1s being present, then 0, then a negative number of electrons or G1s. No, you can't have a negative number of electrons. They can't be. So I changed the scale. I shifted these numbers down to this and redid this curve here. And so it starts at a midpoint. The midpoint somewhere, it may be exactly at the midpoint, or it may be somewhere else, doesn't matter. It has a midpoint. It goes to 0 and then to plus 10. It has a minus 5 to plus 5, excuse me, is a range of 10. But in the ear, I'm suggesting that because of the atmospheric pressure on your ear, you have atmospheric pressure on here, 14.7 psi, pushing this way, varying a little bit. Even if there was no sound in the room, there's always a little bit of variation. And what I'm saying is the signal sent to the brain is a steady state stream of G1 particles, in this case with a value of 5. That's just an arbitrary number, it's not a real number, but it has a steady state number varying slightly around that value. And then, excuse me, and then when a sound wave hits and pushes in, when you get an increase of pressure, they told me in the previous video that the basilar membrane, and this is what I'm trying to represent here generally, is the basilar membrane goes down, and then when there is a decrease in pressure, the inside pressure of your head pushes the eardrum the other way, and you get a decrease in pressure would move the basilar membrane up. Increased pressure moves it down and moves it up, and in the process sends these signals. That would be my contention. That's exactly how it works. Well, this is a picture of they sliced the cell so you could see what it was like, and this is an artist's drawing, and this is the hair bundle, which does the basilar membrane. It moves up and down, causing this to move back and forth, and the way it does it is that at the top, if I can, this is not going to work well, The top of it is this way. Let me do this. Okay, so you have the tectoral membrane at the top, and you have the hair cell membrane here. I'll put it right in front of my face. And normally, when it's in its natural position, there's very little contact, just enough to be touching. When the basilar membrane goes up, it pushes this way, causing extra pressure. And when it goes down, it's less pressure. Pushes up, more pressure, less pressure. When there's more pressure going up, there's more G1 particles being released. When there's less pressure, there's fewer G1 particles. I'm sorry, my hand didn't do very well there, but the whole idea was that you have more pressure one way when the sound is coming into this ear. There's more pressure this way, and there's more pressure at that point, releasing more and then less. It's my idea. I didn't read that anywhere. No one has indicated that that's what it is, but that's one way it could possibly be. And as you get more pressure, you get more G1 particles flowing down this way. Somehow they're guided, bound, and make it through to here and get sent to the brain. Okay, well, that's my explanation, the mechanical explanation. The G1 particle explanation is the pressure that causes high pressure, more electrons, more G1s, low pressure, fewer or none. Okay, got to get the next picture. Now I'm going off into something different. While I was looking around to find information, I stumbled on this link. This is just a text with pictures, and they were talking about mechanical computers, and when you scroll down far enough, I found this, a mechanical harmonic analyzer. This was the text about this. I don't think this is Mr. Michelson, but the scientist and Nobel Prize winner, he won in 1852. Mr. Albert Michelson is known and has been awarded for his work on the speed of light measurements, very often called the Michelson-Morley. He worked with a gentleman named Mr. Morley, Michelson-Morley experiment. In a sense, they got a null result. We were trying to prove that ether exists, and they got a null result, and as a result, a lot of people dropped the ether. But it's not so well known that he had developed a mechanical harmonic analyzer, a machine that can perform Fourier analysis and synthesis, a mechanical device that actually demonstrates it either way. And yeah, there are different configurations of the same machine. You can see a cone here that would obviously represent a low frequency here and a high frequency here, just like the cochlea. I'm not saying that that's precisely the same thing at all, but I am saying that if you can build a mechanical machine that can do a Fourier analysis, then clearly the tongue can do it, and they can both be mechanical in nature. At the same time, I stumbled on an interesting video that explains in detail how it works. It has 4 different videos on how this mechanical analyzer in particular works. And the cochlear ear works very much like this. Besides an introduction, which is the first video, the second one talks about synthesis, and the third one about analysis and then the operation. A very nice description of how a mechanical analyzer can do Fourier analysis and Fourier synthesis. The last thing I want to talk about today is that third video, the presenter describes the fact that the force versus displacement of the hair bundle is not linear. It's not linear. You would expect it to be linear like this dotted line. But here's the force, and this is a positive force. Well, you might call this a negative force. I'm calling this a force in the x in this direction, and here's the force in that direction, which is exactly what happens on the drum. The drum gets a high pressure from the air, pushes the drum one way. When it's low pressure in the air, then it's the internal pressure of your body pushing the drum the other way. Pushes this way, pushes that way. So this is, to me, is direction, not value, not plus, not minus. It's direction. And as it does this, it should be linear. But what they found, and they've done this mechanically by actually pushing on these things, they find that there's, as the force goes from 0 up, it doesn't move as quickly as it's supposed to in a linear direction. It's slow to move, and so it's offset this way. Same thing happens the other way. So what you have here is a distortion in your ear in terms of hearing sound as it goes from, as the force changes from this to this right here. You don't get a precise reproduction. Well, he then shows this one. This is quite interesting. You really want to go listen to this because you can do this right there online. When you get to this point in the video, he explains that if you play this tone by itself, this is 1100 hertz and then linearly decreasing in sound. You play that by itself, you hear that. This is 700 hertz, and you play this sound, and you hear that. And so you have the audible sound coming into your ear this way. First one, then the other. But when you play both into your ear, and you're only getting two into your ear, because of that nonlinearity, you'll hear 3. If you listen to the video that they have, they're going to generate these 2, and you're going to hear that in your head, even though this is all that's generated. The interesting comment he makes is that composers have decided to use this feature in composing music to get unusual effects, presumably, and hopefully pleasant sounding, but a unique type of music. Interesting point. Should watch it and listen. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.